Hello guys, welcome to another video. So in this video we are going to learn about the chain rule, and as you know, in the previous lectures we have also learned about the derivatives and how to solve the problems using limits. So let us just quickly recall all the things that we have learned. So I'm going to write down the things we have learned in both limits and derivatives one by one. So just to recall and have a review of what we have learned. So this result, as you remember, it was limit x tends to a x to the power n minus a to the power n by x minus a equals to n into a to the power n minus 1. These two limits are almost the same kind of limits because, as you know, when we proved them using the Taylor series expansion of the functions log of 1 plus x and e to the power x. So that's why I'm writing them simultaneously. So these two limits were also there. Then we had the limit involving the sine function, which was limit x tends to 0 sin x by x equals to 1. Now we have improper limit as follows. And this is equal to the exponential number e. Right, so this completes the basic definitions for all the results on limit. And now the definition of derivative, just to recall. So the derivative of a function at x equals to a is given by f dashed a equals to, there are two definitions, I'm going to write both of them. X minus a, this is in turn equal to limit h tends to 0 f of a plus h by h. So these are the two definitions that we use in order to find out the derivative of a function, which we also did in the last lecture. We found out the derivatives of e to the power x, sin x, cos x, and in this lecture obviously we are going to learn about the chain rule, and that would actually change the way we look at derivatives. It would be pretty easy now to evaluate derivatives using what I'm going to tell you. So this was done, and we also did a few basic derivatives like ddx of sin x. So anyways, let us begin with the chain rule. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u where g is a function such that it goes from d to u and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dash of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down, but then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend, but when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that, but you're just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log, so layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now the answer can be written directly if we have that in mind, because we differentiate one by one and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it was the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x, e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x, because the differentiation of a constant is 0. And if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x. So 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x. So 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously it's a multiplication in between. So this is our final answer for the problem. So as you can see, sometimes these problems can become a bit more challenging, but we do know how to deal with them once we know the chain rule. In the next sections I would be trying to introduce you to chain rules and more problems from derivatives, and then we will be solving a lot of problems in derivatives. Once we are done with that, we can move on to basic integration, because as far as I'm concerned, limits and derivatives both have been touched a little bit, which is only what is required to get on to continuous random variables. So we will be ready to go to continuous random variables after that. So thank you for watching, and in the next video we shall be practicing about derivatives and their problems. So, and do not forget to check the app link in the description, which is the Breatter's Math app, which is a mathematical app where the theory regarding to whatever I'm teaching here, these videos, have been already put. So you can consider that. You can also give your feedbacks there and get answers from me directly there. Thank you.